Okay, let's get started. You can turn in the homework project, last homework project up here. Yep. You can pass it after the class. Right? So most of you should have all the assignments and stuff graded till now. I have 4 of them here. I don't think the paper are here, right? So, yeah.
On that note, if we have corrections for the past homework, make sure that you after that.
Yeah. You saw the email about the 2 questions, right? So for people who got the questions today, if you have any questions, talk to me after class, right? After class, or send me email, right? So today I'd like to go through, finish a little bit of what the servers and stuff, and then go very high level over Windows XP, right? And these are more in the model of trying to give you a sense of what real life operating systems are, kind of thing, right? And one thing we didn't touch upon at all is the notion of data centers, right? The world is practically moving towards a data center model. There are few holdouts in terms of like Notre Dame has its own website, data centers and stuff. But realistically, you want to move into a model where it's you put in a big room, a whole bunch of computers, sort of like the picture they have here, but you put a really big room, a whole lot of computers, right? Because if you read in the popular press, I think Google bought like $600 million worth of data center in South Carolina, North Carolina, wherever, right? So wherever they can get some power plant and wherever they find cheap land, they put up one of these data centers, which essentially has one of the, if you look at these, if you can see the picture, essentially you have a bunch of computers put into a big rack, and if you notice on the floor there are holes, so the air conditioner comes, the cool air comes through the bottom and then goes up to the top and stuff. So there's a lot of work trying to reduce energy of these, because for every watt the computers consume, you need a watt of cooling power, right? So when you're talking about, so I think like some of them want to run off of a 300 megawatt power station going directly to the data center kind of thing, right? So when you're talking about megawatts of power, anything you can do to save the energy is a big deal. So there's a lot of work trying to figure out how to do the air circulation in these systems. So it's not what the servers used to be, where you put AC, you put as much AC as possible, keep the room cool and stuff. When you're talking about millions of nodes, these are a big deal, right? And most of the companies do them. Amazon has one, AOL has them, and all those things. You don't hear much news about it. In fact, I don't think that if you go to these sites, you see a big sign that says, yeah, here's a big Google data center, for obvious reasons, right? I mean, these are critical infrastructure, so you don't want people to know that if you want to disrupt Google in a small way, you want to disrupt these things, right? So these are some of the hardware, how the power of those things are. The real reason how these things happen in a companies are, most of the systems, they operate on a 3-tier model, right? So they have a production system, they have a backup system, and a test system. So if you want to deploy a new service, you test on the test site, and then move it to the production server. And so you would have 3 times as much as you need. So you need one which is serving the world, one which will take over when the main system dies, and then you have a test site, right? And the requirements keep changing, right? So most of the world is on the web kind of technologies. So if your site suddenly becomes popular, you want to add as much computing as possible, and that's one of the reasons why data centers are interesting, because you as a customer will want to say, I want to be able to serve any request with certain latency. If that means that suddenly I'm becoming popular, means I need lots of computers, you got to find me something, right? So different companies have different terms for it, but essentially the idea is on-demand computing. So if you talk to IBM or HP or one of those, they get really happy talking about on-demand computing, right? So where based on the computation, you get more data, right? And one of the other stuff which we never touched upon at all is the notion of a service level agreement, right? Which is a very important on these systems, which basically states that when you sign up with these data centers, sort of like your ISP. You sign an agreement which says that these requests should be serviced within 5 milliseconds. These requests should be serviced within certain bounds. And if those are not met, then there's a penalties, right? So that's how you get business. So you basically say, I will run this service for you. It'll be up at a certain rate. It'll be giving you service at a certain rate. If you violate any of those, we'll have to pay a penalty, right? Which may mean as simple as you don't pay for the services, or as bad as you have to pay us money, right? So if you are Best Buy and suddenly your site is gone for a day, right? Or one of those big companies, then you lose a whole bunch of money. So you need these service agreements. So it's not best effort. It's not, we'll give you the computers, and if it works, it works. It doesn't work, right? What that means for us is those notions have to be built into the operating system. So the operating system cannot just service different processors as processors. It has to know, in some sense, that these have certain agreements, which means that the scheduling would have to prioritize those differently than the others, right? And it's not clear how we will go there. These are active areas of research, and these came about within the last 5 or so years. But companies spend lots of billions of dollars in trying to get there, right? Trying to get where it's on-demand computing, trying to get where you can guarantee the service that the service agreement gives you, right? Which does not mean that you give more service than what the agreement says. So if the customer service signed a document which says you have to give us 10 millisecond latency, right? The data center providers do not want to give you 1 millisecond, right? Which is 100 times better than, in some sense, better than what the customer asked for, which will be good for the service level, but then you'll be losing money, right? So you want to give no more than what the service contract is, and then work off of that, right? So you have to move. So a lot of work trying to figure out how you negotiate these things, because these are legal documents, and then how do you represent that within the operating system so that the scheduler can use that to figure out what to do, right? So there's a whole bunch of work, and that's an interesting piece of work. Whoever can solve that is these technologies are worth billions of dollars, right? So ideally, they would like it so that nobody has any computers, right? You basically have all these things running off of data centers, right? Many of you may use one of these things, right? How many of you use like Yahoo Mail, Google Mail, or any of the Google services? Or like Google now has a Google Word, Google Spreadsheet, and all those things, right? They all run off of some data center which you don't know what they are, right? And right now, what's the service level agreement that you guys get from Google for any of those? You did sign something, right? When you signed up, it says like something that it says accept, deny, right? How many of you read those?
You get Gmail for free.
Yeah.
So then they don't promise anything if you're not paying anything.
Yeah. Yeah, but they say it in a legally fashion that that we don't say anything, and nobody complains because it was free, right? How many of you actually have paid one of those services? Like I think Yahoo and all gives you paid email, right? So if you do have one of those, right, then I bet you will read that carefully, right? So now you expect it's free. What do you expect, right? But when you pay for those, you expect the service to be at a certain rate, right? Whatever you think is fair, and how do you interpret those, right? Actually, a lot of schools are moving towards that model. Like you hear about some schools which are completely getting rid of all Word and all those things, moving everything to Google, right? And give that to their students, right? Because the perception is you save a whole bunch of cost, right? Because the main cost of managing all these systems is in managing these PCs, right? So how many of you have taken a course in data system administration or one of those courses? You'll probably take a course that Kurt offers, right? So that talks about managing the system. So OIT's main job that they do, other than what they do in the back end, is to make these things work, right? They have to make sure that these things are certain things. So they have policies and stuff. So one of the things you may notice is when you log in here, save files on the local disk, it gets wiped out, right? So this machine is, even though it's a Windows XP independent machine, is practically powerless, right? Because it's being managed somehow. So the management cost is a big deal. So if you can manage like tens of thousands of these moving away to server, companies think it's a good thing, right? So that's the notion of what is called autonomic management, right? Which is another thing that IBM calls it. I think every company goes through a different term for this concept at different times. I think they used to be autonomic. It may be called self-healing and all those things. So what they would like is when the systems fail, when you have large number of things and the systems fail, they should fail and recover nicely, right? That's sort of the big level notion. So if you have these desktops, I don't know how many OIT has. Let's say OIT has like 5,000 of those, right? You have to expect that some of them will fail at some point, right? Either hardware or the software or the set of installed application, all those things. You would like them to somehow magically heal themselves and go on, rather than somebody has to call OIT, they have to come over and then fix those, right? You can do those for 5,000 machines. When you talk about the Google data center, where they have 100,000 machines, right? You can't expect somebody to go in and fix each one of those. So how many of you heard the term autonomic computing, self-healing, all those things? If you haven't, if you go to a company, those are terms that's the very important stuff, right? So what they would like to do is companies would like to outsource all their computing to these data centers, sign these agreements. So you're still working through what that means. How do you specify what you want, and how do you specify how you get paid, and how do you specify, how do you know when those are violated, right? And servers have a whole bunch of, the data centers have a whole bunch of these machines. They have to manage their resources to give you based on your agreement, right? So they have almost infinite resources, but not infinite, right? So they have to manage how much they give to you, how much they give to another customer, right? And if one of those things fail, how do you recover from those and keep these things going? Because these are lots of those. And how do you add new stuff, right? And those are all the stuff that those are the harder thing that to worry about. And all of them, operating system is involved, because that's the one which does this scheduling, right? And you have to worry about the cooling too, which was not a big problem before. But when you're talking about 300 megawatt power station feeding your data center, cooling those massive things is a big deal, right? So some of the things that I've seen the HP labs, they do those stuff is basically have this whole room, right? It's basically a smart room, right? So it has baffles, sort of like the stuff you have in your apartment, right? Where the heat vent stuff, right? So it controls based on which part of the room is hot and open the right baffles, so you get the cooling, right? And it's not as trivial as that, because just because you open somewhere doesn't mean that you get cool in the right spot, right? So you need to control, because the fans are running, it's sucking the air through the whole stuff. So there's a lot of modeling trying to figure out how in the 3D space temperature flows, I think, which is more of the physics, mechanical kind of stuff, right? How do you do the heat transfer in this whole room? And how do you optimally manage these baffles such that the room is at the right temperature, right? You don't have to keep the computers running at 55 or something, right? So they want to keep it at 65 or 75 or something. And you have little robots running around with temperature probes all through the height, right? So you can move up and down to figure out where the temperature is and measure the temperature. So, because remember, data center, if you look at the picture, there's computers all the way to the ceiling, right? So it may be cool down here, but it may be hot up there. So it goes around, make sure that temperature is fine. And many of these rooms, you like to get the oxygen out and then run helium or some other gases which are good for the computer. So you don't want human beings to go in there, right? It's pretty disruptive, right? So it looks very science fiction kind of stuff, because you have these robots running around measuring the temperature. And ideally, you would like these things to be self-healing, whatever. Some AC fails, then the systems all move all the computing away from that corner, move it to different areas and stuff, right? We are nowhere close to that, but that's an area of research that people are working on, right? You don't see too much of those in the academic setting, because we have the department probably has 100 computers or so, right? We're not talking about this kind of numbers, right? How many of you seen those data centers? Even a small one? Where do you see?
Where I'm doing my internship this summer.
Okay.
Company in Indianapolis.
What's the company?
Blue Lock.
Okay.
Just started in February.
Is that a data center?
Well, what they do is infrastructure as a service.
Okay.
So.
Hey, Dave?
Yeah, it's like I've written it. It's a data warehouse
Okay.
in Dallas that the company I work for uses.
Okay. Yeah, there are a lot of companies doing this kind of stuff. I think in South Bend there's a company called Pinnacle, right, which is out in Mishawaka, which does this sort of a thing, right, outsourced to the stuff, right. So what I don't know is what happens. So since they can outsource it from here to South Carolina, because it's apparently cheaper to have the energy there, I wonder what happens when they start moving it around, right? Because it seems like the right place to move all this stuff would be to Arctic somewhere, right? Then remove the cooling cost by putting it into the ice, right? I'm sure they're doing it, right? Because why not, right? So, which doesn't sound good because they're generating 300 megawatts of heat. Would mean that they're melting all the ice, right? But so those are the hard research areas. The energy management, which most of you look at it from the laptop perspective, but it's the server side is just as important, or even more important, because these things generate so much heat that you want to keep the cost down. And the one stuff we didn't really talk about is the virtual machine, right? I want to actually give that as your homework project 5, but it's still not easy, right? I mean, the way you set it up, some of you may have set up one of these things, but if you want to set up Zen, it basically boils down to giving us a setup like, do this, do this, do this, do this, do this, do this, and that's it, right? There's nothing for you to think, so maybe later. But if you want to try those machines do support Zen. The operating system does support Zen. And the idea of Zen here is, how many of you use one of these things? Zen, VMware, Palace, one of those things? Right?
I'm using it this summer.
Okay. So one of the things that these guys like to, one of the nice thing is you can. So essentially you are running another operating system inside your own operating system, right? And the operating system inside does not know that it's running under a virtual machine. It can by figuring out the timing, right? But otherwise, it's supposed to look like a different one. So you have, so you can run your main Linux, and then you can run your XP, and you can run another XP, and you can run another Linux, right? You can run these 3 virtual machines, and this one looks like it's a different machine. It needs hardware support to make some of this happen, right? But most of the new Intel and AMD processors do have those. So you run these machines, and so for this machine, it's as if it's living on its own, right? So it has to have its own network virtual card. So there's this operating system running. So this operating system may, through some mechanisms, look to see what's going on here. But for the most part, these are independent, right? If this wants to talk to this one, it has to talk as if they're different machines, right? The reason why a lot of these things are interesting is, if you have to do this manually, if any of you install this stuff, it's painful because you have to install a new Windows operating system inside here. You have to install the whole drivers, keep them secure, and all those things, right? But the more interesting stuff is you install whatever operating system you want into one of these containers. You create you save the hard disk state, right? And then I give it out to everybody, right? So you have then what you have called player, right? Which takes this image, right? Which has all the software that you install, and start a new virtual machine on those. Does that make sense? You essentially install the operating system on a virtual hard disk, and then you make a copy of the virtual hard disk and give it to different virtual machines. And this is very similar to what you did for your homework project 3, right? You created a file system inside a file, and you make copies of the file. So if you create your file system for homework project 3, right? Create a file system, create lots of files, and then kill your process, and then make 10 copies of your file system, and you run 10 different applications. Each one of them will have their own, will look like you created the files for them, right? So the nice idea is once you have this stuff, you can run a virtual machine on the stuff, right? So if you go to any of these websites, they sell you these appliances. They sell you ones which do whatever, right? So you can think of one being like a Word container, right? So I download the stuff, and if I run a new virtual machine on this image, then I get Word for free, right? So as a data center, they can have these like images, right? And if they find out that this machine has a capacity of 5 VMs, right? The machine can support 5 VMs. It's only running 3 right now. They can create 2 Word ones, right? To run on this machine, right? And then suddenly they find that the machine load is too high. They can stop it, move to a different machine, and start it on the new VM, right? So they can actually move it across the machines very easily, because all you get is a virtual machine, and it's up to them to figure out where a virtual machine runs. And whatever you do in here won't affect anything here. Whatever you do in here, you can't see anything in here. So this could be running GM's Word. This could be running Ford's Word, right? They can't see each other's file, right? They can be running a program which tries to figure out how to destroy Ford, and Ford can run something which destroys GM, but they won't know they're running anywhere at all, right? And it's up to them to prevent this stuff, right? But the virtual machine concept lets you create something like this, right? But I can create this. I can create as many virtual machines as I want, because I create this one master virtual machine. And anything which is running, I can create clones of them. I can move them around different machines and so on and so forth, right? Of course, these are resource intensive, right? But resources are cheap these days. So we couldn't do this like maybe 5 or 10 years back, but now you can do these things, right? So they love this thing because they can then farm this out to as many stuff as you want. So that's part of the on-demand computing. So if you want 2 more machines, I don't create 2 more machines. I create 2 more virtual machines using the images that you already gave me, right, which has all your software, all the stuff installed. So I start a new virtual machine with the image that you gave me, and bang, you have it, right? So this may be running a web server with all the tools that you install, and you have copies, right? If these are not clear, let me know. I mean, these are stuff that the companies are working on, and some of you, when you go to internships and stuff, may see some of these stuff happening, right? Essentially, that's so from OS perspective, all the stuff we talked about was here, right? But anything inside here is also operating system, and it does its own management and stuff like that, right? And in terms of the grid is another, grid cluster is another popular stuff. So grid is more of a concept. It's implemented using things like these, right? And the notion of autonomic manageable stuff, right? So many of the companies really want this stuff, right? It's kind of hard for you to imagine because you are used to dealing with few of them, right? If you're dealing with 4 disks, you run them in RAID, right? If you have to run with 4 million disks, right? Which is what these guys are operating on, right? So one of the project at CMU, they were trying to figure out what happens, how often do you have to replace these things, right? If you're running with like 10,000 hard disks, I think the probability is 1 hard disk will fail every hour or something, right? So you have to hire somebody whose job is to go around the different stuff and figure out which one crashed, replace them, right? Doesn't sound like a very fun job, right? Your job is 8 hours. You just have to like replace the hard disk and put the new hard disk in. You replace the hard disk, right? And so you can't prevent the hard disk from failing because that's part of the hardware stuff. But you have to be able to do something where you don't have to have a human being going across and stuff, right? So that's the big picture of where the operating systems are used in the rest of the world that you will see when you go to companies and stuff, right? And if you have any questions about those, we can talk offline on where the things go. And I think some of the classes you take in the senior level classes will cover some of these things. If you take grid computing or system administration, all those things, they may touch upon a little bit of those, right? And again, the problem is we have never seen any of those in our real life because we deal with such a small level of computing, right? So I want to go a little bit over what Windows XP is and what it does, right? So how was the homework project 5? Was it helpful? Was it? So now I think last class when I asked, only a few of you had looked at the file system code, right? Now that everybody has looked at it, what is the impression of the code?
Needs more comments.
Needs more comments? Okay.
It's kind of cryptic.
Hmm?
It's kind of like hard to read. They use really like abbreviated names.
Okay.
It's
So,
almost obfuscated.
okay. So like I said, I mean, this is the file system which is used a lot, right? It's being looked at by a whole bunch of people across a whole lot of years, right? So there's nothing to do with the operating system, but it goes towards the notion of open source software, right? If you find this hard to read, right, imagine anything else, right? This is the one thing where everybody would have looked at it, right? And there are more obscure parts of stuff, right? So you understanding the context of what things are and being able to change and improve stuff, right? Right. So this is one of the reasons why I didn't want the homework, the one on Fuse, right? I think compared to looking at the real kernel, Fuse is a lot easier because it has its own quirks, but it's mostly your code. It doesn't have to integrate with the other stuff as much as you would do with the kernel stuff, right? In terms of the comments and stuff, the only OS I've seen which has really lots of comments is Data General. There used to be a company called Data General, which many people bought it. I don't know who owns it now, right? They had a Unix called DGUX, right? It was very well commented, right? It was commented to the point of being annoying, because what would happen is, so I think they use some sort of a software tool which shows different levels of comments at different levels what you're looking at. So I'm just making this up, right? But let's say if you have a comment like this, I think the tool picks it up at certain level, right? This I'm just making it up, but you have like 2, 3, 4, 5, something like that, right? So depending on the level of importance you want, you can have those things, right? And so you never use a variable like I equals 0, right? Because I has no, I mean, you can't tell what I is for. So they have some conventions. I forget what they are, but let's say int, right? Something like you look at the variable, you know that this is from function, it's an integer function. Actually, it will be more specific, like integer, 4-byte integer function. It's being used as an index. It's used on a func kind of thing. I'm just making this up, but some sort of like this. So you look at the variable, you can tell what it does, right? So it may say equals 0, right? Or it may say like 0, because different hardware has notion of different as 0, right? Like for example, null. You know what null is, right? What is null?
Similar to the 0 memory address.
No, it's not actually 0, right? It's null is invalid memory address. But you're free to define a new machine where null is something else, right? 0 may be valid, right? I think there used to be machines which did that. But if you go to that machine now, many of your code will fail because people assume null to be 0, but it doesn't have to be. Null is invalid pointer, right? So anyway, so they have stuff like this. And then you have like comments, right? Comments at level 1, level 2, level 3, level 4 kind of thing. So you look at this one line of code, right? Which in normal human programming would say I equals 0, right? Many of you write code like this. I mean, at least I write code like this, right? Many of you write code like this, right? Essentially going through the index and you're setting the matrix, from 0 to the whole matrix, you're setting it to 1, right? You can never write a code like this in that model, right? You will have to define what this I is, define it somewhere, and then you have this stuff. So this line of code would become like, 5 pages worth of fully commented code, right? Yeah, it's very well commented, but it's very hard to read because unless you have the tool to figure out what these are, unless you know all the conventions, right? So people hate that, but then you get into, was the book helpful? The Linux book?
Yeah.
Right? It was on the reserve, right? So that's a helpful book to figure out what happens, right? Anyway, so Yeah, I would like to have a chance to look at the operating system, but operating system is both easy to look at compared to other horrible code that you look at in your life, right? So many of you, when you go to companies and stuff, you look at other code. This is one of the examples of a good code, right? And you're going to see lots of bad code, right? So you get lost in all the details and stuff. So anyway, so do you have any questions so far before we look at Windows XP? So Windows XP, I think this is chapter 22 in your book, right? It goes through a little bit in a high level of what Windows XP does. And if you look at the contents, you'll notice that this is not a Windows XP that you know about, right? The Windows XP people know about is the Win32 API, not the operating system, right? And we'll see what the difference is. But the Windows that you look at is the GUI with the start and task and all those things. That are not the operating system. That's the user interface. That's the windowing system with the Win32 API. And what we're going to talk about is the underlying operating system, which was inherited somewhere from Windows NT to Windows 2000 to Windows XP to whatever, which I don't think it has changed significantly since the Windows NT days, right? All the stuff you see is the top level, but the underlying stuff, of course it evolves, but not as drastically as one would imagine, right? So yeah, it's a 32-bit preemptive multitasking operating system, right? And now there are multiple variations. One of them has a 64-bit variation. So some of the newer kernels have 64-bit variations, right? So what would take to change a 32-bit operating system to a 64-bit operating system? Thinking back at the different modules we looked at, what would be the implications of changing from 32-bit to 64-bit? Why can't they just create a 64-bit operating system without going through all this hassle? Or without making a big deal about it, right? You can write a code like this, right? Suppose you wrote a program, right? Suppose you wrote a small function like this, right? If you go from 32-bit to 64-bit, nothing happens. I can hold more, right? But your programs continue to work, right? But if you look at the popular press from all the companies, they make a big deal about going to 64-bit operating system, right? So what are some of the issues that you will face thinking about what we've seen in the class? Yeah.
Become maybe a problem with like shifting or perhaps typecasting.
Yeah, many of your code which assumed, if you wrote a code which is assuming shifting left and right, those will fail, right? But those are the application side, right? So operating system should not have to worry about it, right? What else would change? Yeah.
We have to have some implications for the memory hierarchy. Now you've got 64 bits easily accessible in a register, so take advantage of that somehow.
But what would that? So it's using more memory, right? So why would that be a problem for you? Like why would you? It can use more memory, right? But you don't have to, right? If you wrote a program which only used 32-bit, it should work fine with the 64-bit. There's no reason why that should fail, right? So here's a hint. Think about file systems, right? Is there something that would change when you think about file systems? A 64-bit file system, right? Yeah.
You might change the way the size of blocks, the block size, or the way blocks are addressed. Those sorts of things.
You could do that, right? That also depends on what your hardware disk does, right? You'll most definitely change the offset value, right? Remember the file pointer which keeps track of where you are, right? You'll have to change the offset value. Now you can go further out, right? So now the files can be bigger than 4 GB, which is what happens in your 32-bit, right? What that means is if you want to use more, all your file system API would now have to move to the next model, right? So what would mean is your seek would have to take a 64-bit value, right? Which may mean that some of your older code may fail. So that's why what they do is they have LSEQ and LSEQ64. If you look at the modern operating system, they have LSEQ, LSEQ64, Open64, right? Because the seek now can go further. Your memory, stuff like that, right? There's some things that you don't notice. There's some things that will fail, and stuff like these, you can't just say I'll pass a small 4-byte integer, because the function would fail. It can't figure out which one you're calling, so you would have to do two different stuff, right? So for now, so when you think of the x64, Windows XP 64, right? It's 64-bit kernel by using these kind of functions. It's not a true 64-bit machine. It's a 32-bit machine operating system with a little bit of 64-bit function calls added in, right? So XP comes in a number of different variants, Pro and Media Center, Home, and all those things, depending on what features are turned on and off and stuff. What is not widely known is that it's a microkernel-based architecture, right? Which means that there is a small kernel which does all the stuff, and then there's all this stuff on top, right? Which is what you notice most of the time. And it's designed for a whole bunch of stuff. It's designed to be POSIX compliant, which is essentially what you get with your Linux. So it should be able to run your Unix or POSIX code with no change. It should be able to run DOS. It should be able to run Microsoft Windows, which is the GUI, Win16, Win32, that API. And it has a whole multiprocess support, secure, and all those things, right? And so the notion of microkernel says that you can add new functionality without changing the base. You have a strong foundation, and you can add different stuff. I think the next slide has a graph which shows what they are. But the more important stuff is XP is very portable because it's written in C or C++, right? So if they really want, they can move it to any architecture they want. They're not as wedded to Intel as people believe, right? In fact, Intel, the NT used to run on DEC Alpha for a long time before DEC and Compaq and all went away, right? So can you see this in the back? So essentially, this is the organization of the Windows machine, right? So when you see the Windows Win32 subsystem, so anything above the dotted line is the user mode, right? And under here, that's the operating system, right? The one in the middle. You have the hardware at the bottom, and the stuff at the top, right? Which is what you interact with. And so most of you would use the Win32 subsystem, which defines the system calls and the API by which you talk to the operating system, right? And so they define it. So they have different variants of the Win32 API. So you can run MS-DOS applications, right? MS-DOS application, I think, is only 16-bit API. So it goes through a virtual MS-DOS. If you look on the second box from this side, right? So MS-DOS applications go through the MS-DOS VDM and call the Win32 API, because Win32 is a superset of MS-DOS functionality. And it's same for Win16. Win32 applications directly interact with the Win32 subsystem. OS2, which is what Microsoft started off with by working with IBM and all those things, has its own system, right? Then you have the logon process and all those things. So if you notice, there's also the POSIX subsystem, which is what you need for Unix system calls. So if you write a C system call, you would go directly from there to the kernel. If you're using Win32 API, you'll go to the Win32 subsystem, right? So that's the stuff you see as operating system. So that differs from, in a high level, in Vista you have a different stuff up there. In Windows 2000 you have different stuff up there, kind of stuff, right? So I'm not going to talk about that component, which is what you interact with. What is more important is the operating system which runs underneath, right? The operating system is considered to be a microkernel because it does not implement any of those stuff that is up there, right? So it does not implement the notion of, so one of the things is when you have processes, remember the notion, the processes have a parent-child relationship. When you do a fork, the new process is called a child, right? That notion is not known to the operating system, right? This operating system does not know anything about processes being parent and child. that is implemented in your POSIX subsystem up there. It knows as two different processes, right? In fact, it only knows as threads. So it knows a bunch of threads. It manages threads, right? Notion of processes is a POSIX kind of system. Notion of processes with parent-child relationship is a POSIX system. Those are not known by the kernel. So you have a lean kernel, which all it does is it deals with threads, it schedules threads, and it's up to you to figure out what to do with those threads. So it does. It's object-based. The security system is pretty strong. So essentially, everything is object. You operate on objects, right? You pass these objects around, and you can clone and create new objects. And the security mechanisms will mean that who has access to the object, right? And so those two are part of the operating system, right? The process manager runs, schedules processes, in this case threads. Plug and play manager defines what happens when you add new stuff. So when you plug in a USB key or something, you'll load the corresponding device drivers to deal with those. You have a virtual machine manager and a local procedure call facility, which lets these modules talk to each other, right? So that's the notion of the stuff. So essentially, the stuff you have in the box is called the executive, right? It implements functionality which is very crucial to the system, which is have threads and schedule them, have notion of I/O, right? I/O manager, caching, all those things, and the virtual memory monitor, which interacts with the I/O system, right? So if you think of it as the different modules we looked at, right? The I/O manager would be module 4. The virtual memory manager would be module 3. The process manager would be module 1 and 2, right? With the local procedure call letting you talk to each one of them, right? So that's the executive, right? That's common for anything. So you could technically run Mac OS X on top of this if you build the appropriate stuff in the user space, right? All this is inside the kernel space. They all interact with the kernel, which makes these happen, which is much simpler, which is down there, right? You see the little box. And they interact through the hardware abstraction layer, which is the HAL, right? Which abstracts the hardware so that when you port this operating system from Windows, Intel box to PowerPC, you would replace the hardware abstraction layer to the PowerPC, right? So they can port it to any architecture they want by essentially replacing the hardware abstraction layer, which abstracts the hardware components to what the OS can look at, right? So any architecture you could think of, they should be able to replace that component, right? And the kernel builds on top of the abstraction. So, of course, they depend on machines which have virtual memory and all those things, because otherwise you can't implement virtual memory efficiently without those, right? But on any modern machine, they should be able to port this stuff. And of course, there's a graphics driver hanging around somewhere here, right? That was like a very 2-minute overview of what Microsoft has been working on for the last, I think they started this on 88 some time frame, right? Here, what they've been working on for the last 20 years in 2 minutes, right? So that's the stuff, right? So, if you look at it again, they really thought this through when they built the system, right? Because the hardware abstraction layer abstracts it to a modern operating system, right? So when they have a new architecture, they have to just replace those, right? And the kernel is small, and kernel does what it has to do very efficiently. And I don't think that component has changed a lot for the last 10 or 15 years. I mean, of course, you tweak it, you make it things better and stuff. It does not implement policy, right? The policies are implemented up there. It implements mechanisms. So it implements mechanisms to schedule threads, right? The policies are set by the user level stuff, right? So when you use Windows, you're really using Win32 API, which sets the policies on what should happen, right? It sets policies on where the window should be, where there should be a start at the bottom and all those things. It defines policies on who gets priority, right? It defines policies that I/O bound tasks get different priority than something else, but the kernel does not care, right? So you could technically run any number of operating systems on top of it. the security architecture that they have at the executive level is pretty strong, right? Each object has its own security. It's object-based system, right? It's a lot more cleaner than what you see from your Linux-based system, right? You can't just pass the. So when you create a new task and when you have a thread and pass it to another thread within the kernel, unless you have authority, you can't change anything, right? So one of the ways that they can do that is they can keep the MS-DOS from destroying the Win32 half of the system, because depending on what privileges you have, you can't change the stuff, right? So if you look at this architecture, and this is all you know, and you never use the operating system, this system is lot more secure than your Linux or any of the or the other ones, right? So why do they get so much flack? Why do people complain so much about? Yeah.
Because you're not able to manipulate the policy part of it to make it flexible for your needs.
Yeah, the problem is the policy side, not the mechanism part, right? They can make it really powerful and really well done if you fix the Win32 that component, right? Not this component, right? So technically speaking, Windows XP is a very secure and excellent kernel, right? Because this is the kernel, not the stuff on top, right? But practically, when you get a machine, you get the whole thing, and that may not be as secure as you want it, right? In fact, if you think about it for the Linux too, this is the Linux kernel, right? And the one you top is the GNOME manager, right? You might have seen there are a couple of different managers in those machines. I think run GNOME, right? You think of that as the one on the top, right? And POSIX has the implementation that they do, right?
Yeah.
So Linux is different from GNOME, right? GNOME is an application that's nothing to do with anything. Linux is actually the core machine, right? That is secure. That is secure for what it wants to do. The problem comes in when you add these other stuff on top, right? So I may not have time to actually go through each one of those stuff. I think the slides would help you look into those stuff, right? But essentially, that's what they do, right? We'll look a little bit on Linux on Wednesday. I'll hand out the exams for take-home kind of stuff on Wednesday too. See you on.